most of the weak acids you will come across will be carboxylic acids, the organic acids. So that's the formula of ethanoic acid. And again, when that's in solution, in aqueous solution, it will release this proton, but only a very small proportion of the molecules will in fact dissociate. So what you will get is an equilibrium. So we will form the ethanoate anion. So all that's happening is the H plus is coming off, leaving behind the electron that it put into this covalent bond. So that pair of electrons goes onto there, onto the oxygen. So that gets a minus charge, and the hydrogen ion comes off on its own as a H plus, and of course that would be AQ. And we know that that would combine with the water molecule to give the oxonium ion. Okay? But the point is, for weak acids, you only get partial dissociation. So if we had 0.2 moles per decimeter cubed of ethanoic acid, we cannot assume that that would be the concentration of H+, indeed it wouldn't be. Only a very tiny proportion of the molecules actually dissociate. And that's what determines the pH. Now, the approach to this is based on what you know about equilibrium. It's a reversible reaction. So just like any other equilibrium reaction, we can define an equilibrium constant. I can write Kc, and I would write on the top this one, the ethanoate ion, which I can write like this, CH3 COO minus, and then the H plus, and that would be over the concentration of the undissociated acid. A lot of people forget to tell you that these concentrations are the equilibrium concentrations. It's when it's reached equilibrium. I won't put them in all of the time, but just to remind you, these are the equilibrium concentrations. Okay, and we know the value of this one for ethanoic acid. You get these in your textbooks and data books. The value is 1.7 times 10 to the minus 5, so I can write that up here. So 1.7 times 10 to the minus 5, and it's got units of moles, dm to the minus 3. Now, when the equilibrium constant is applied to a weak acid, we just give it a special name. We call it the acid dissociation constant, so it's normally written as Ka. Okay? And the value for ethanoic acid is 1.7 times 10 to the minus 5 moles per decimeter cubed. You can just check the units. If we just write in the units, concentration of that one, the ethanoate ion, would be moles dm to the minus 3. The concentration of the H plus would be moles dm to the minus 3. And of course the ethanoic acid itself would be moles dm to the minus 3. And so you just cancel down, top and bottom, and you're left with the units of moles dm to the minus 3. Okay, that's why we have such units. Now, there are two assumptions you have to make to calculate the H plus ion concentration. Okay, I'm just going to write the equation again for the dissociation. We've got ethanoic acid, the molecule, in equilibrium with the ethanoate ion and the H plus ion. Okay. First of all, every one of these that dissociates gives one of these and one of these. So we're going to assume that the concentration of H plus and the concentration of the ethanoate ion are both the same. So wherever we see this one, we can just write this one. So I'm going to write at the top there the concentration of H plus and the concentration of H plus. Okay, so that's that one. And all I've done here is write another H plus because I know numerically it's going to be the same concentration of this one. Okay, not always the case of course, but that's one of the assumptions that you make with this method. The second assumption is that the concentration of the ethanoic acid, that's the undissociated, at equilibrium is the same as whatever you started with. So let's assume that we started with 0.2 mole per decimeter cubed solution of ethanoic acid. So that's what it said on the bottle. It's labelled with 0.2 mole dm to the minus 3. The assumption we make is that so little of that dissociates. Okay, so you can almost write it like this. You can say very, very little dissociation occurs. So the concentration of that has not been reduced significantly due to any dissociation. So we can assume that it's unchanged. So what I write at the bottom here is the concentration 0.2 mole dm to the minus 3. But of course, strictly speaking, that's not the equilibrium concentration, it's the initial concentration. Okay, so that's the second assumption. And it's worth remembering these assumptions because in the exam questions they can ask you to calculate pH of a weak acid and then ask you what were the two assumptions that you made in your calculation. One would be that the H plus and the ethanoic ion are the same concentration and that the dissociation of the acid is so little that at equilibrium you can just take the initial value. So this simplifies of course 1.7 times 10 to the minus 5. I'm going to put the units in just to show you how they work out. Equals H plus squared over 0.2 mole dm to the minus 3. What I do advise you not to do, advise against, is just trying to do the calculation in one step on your calculator. Show you're working, that way you're less likely to make a mistake. And if you do make a mistake, get the wrong number at the end, the examiners can always look earlier in the calculation and award marks for seeing that you've got so far. But if you just do it in one big step and you get it wrong, it's harder to do that. So I'm just going to cross multiply. So I've got on this side 1.7 times 10 to the minus 5. I'm keeping the units in here, look, that's moles dm to minus 3. I'll put that in brackets, that way I don't get it mixed up with this one that's coming up here. So in cross multiplying, I'm just sending that one up there. So I write here 0.2 moles dm to the minus 3. And that lot is going to equal H plus squared. Okay, so if I do that on the calculator, 1.7 10 to the minus 5 times 0.2 equals that. So the numbers that I get from that, it's from multiplying 1.7 10 to the minus 5 by 0.2, the numerical value is 3.4 times 10 to the minus 6. If you multiply mole by mole, that's really mole to the 1, so it becomes mole squared. You add the powers, if you like, the exponents. So dm to the minus 3 times dm to the minus 3, minus 3 and minus 3 is minus 6, so it's dm to the minus 6, and that's going to equal H plus squared. So if I take the square root of that, I'll just leave it in the calculator. So if I do square root of my answer, and I get 1.8 times 10 to the minus 3. Square root of that, of course, is just mole, and square root of that is dm to the minus 3 equals the H plus concentration. Okay, so it's very small, and then if I take the log of that, so log of 1.8 times 10 to the minus 3, so I'm just going to keep that in the calculator and just press log and then answer, and I get minus 2.7. Then I change the sign and the pH is 2.7. So 2.7 is the pH of a 0.2 moles per decimeter cubed solution of ethanoic acid. I'll just write that down at the top. If you've got CH3COOH, and it says on the bottle 0.2 moles dm to minus 3, but I make that to two figures because that's what my pH is at, and the pH equals 2.7, okay, which is not as low as what you had with 0.2 moles per decimeter cubed of the strong acid, the HCl. That one was down at 0.7.